Right now, as you watch this, you are moving. Not just in the ordinary sense, not the spin of the Earth, not its orbit around the Sun, not even the Sun's slow arc around the center of the Milky Way. Those are real, and they are fast. But layered on top of all of them is something larger and stranger. A motion so vast that it only becomes visible when you zoom out to scales that dwarf everything humanity has ever mapped. You and the galaxy around you, and the 100,000 galaxies sharing your cosmic neighborhood, are all streaming towards a single point in space at over 1,000,000 miles per hour. And at the same time, everything beyond a certain distance is rushing away from you, accelerating into a darkness you will never be able to reach, no matter how long you wait or how fast you travel. These two facts seem like they should contradict each other. They don't. They are both true simultaneously, operating at different scales, governed by different physics, pointing toward futures that are still, even now, not fully understood. The universe is not a place where things sit still. It never has been. From the very first fraction of a second after the Big Bang, matter has been flowing, colliding, clustering, dispersing. Every object you have ever seen in the night sky is moving, and the patterns of that movement tell a story about the entire history of the cosmos and the forces that have shaped it. To understand why everything in the universe is moving, you first have to understand something that took humanity a surprisingly long time to accept. The universe has not always existed in its current form, and it is not static. For most of human history, the cosmos was imagined as a fixed backdrop. Stars pinned in place, unchanging, eternal. Even Albert Einstein, when he developed his field equations of general relativity in 1915, found that they predicted a universe in motion, and he was so uncomfortable with that idea that he added an artificial term, what he called the cosmological constant, specifically to make the math produce a static result. He later called it the biggest blunder of his career. The first crack in the static universe came from an American astronomer named Vesto Slipher, who in the early 1910s was measuring the spectra of distant nebulae from the Lowell Observatory in Arizona. He noticed something strange. The light from most of these objects was shifted toward the red end of the spectrum, stretched as though whatever was emitting it was moving away from him. A few were blue shifted, meaning they were approaching, but the overwhelming majority were receding, and they were doing so at speeds that seemed wildly too fast for objects simply drifting through a stable universe. Slipher published his results, noted their strangeness, and largely moved on. He didn't have the conceptual framework to explain what he was seeing. That framework arrived in the 1920s from multiple directions at once. Georges Lemaitre, a Belgian priest and physicist, derived from Einstein's own equations the prediction that the universe should be expanding, that space itself should be stretching, carrying galaxies apart like raisins in a rising loaf of bread. Edwin Hubble, working at the Mount Wilson Observatory in California, used Cepheid variable stars to measure distances to nearby galaxies and combined those measurements with Slipher's velocity data. What he found was a relationship so clean it became one of the most important equations in all of cosmology. The farther away a galaxy is, the faster it appears to be receding. This became known as the Hubble-Lemaitre law, and it carried an extraordinary implication. If everything is moving away from everything else, and if you run time backward, then at some point in the deep past, everything must have been compressed into a single point. The universe had a beginning. The key insight, the one that takes a moment to fully absorb, is that galaxies are not moving through space like birds flying through air. Space itself is expanding. The fabric of the cosmos is stretching, and galaxies are being carried along with it. This is why there is no center to the expansion. Every point in the universe sees every other point moving away from it, just as every raisin in a rising loaf sees all other raisins receding. There is no special location from which the expansion emanates. It is happening everywhere, simultaneously, in all directions. The rate of this expansion is described by a number called the Hubble constant, expressed in units of kilometers per second per megaparsec, meaning for every million parsecs of distance between 2 points, those points are moving apart at a rate described by this constant. Early estimates put it at around 500 kilometers per second per megaparsec, which turned out to be badly wrong due to poorly calibrated distance measurements. Decades of refinement have brought the number down dramatically, and modern measurements cluster around 67 to 73 kilometers per second per megaparsec. But that range, small as it looks, has become one of the deepest crises in modern physics. If the universe were expanding perfectly uniformly, with every galaxy moving away from every other galaxy at exactly the rate the Hubble constant predicts, then cosmology would be simpler. But the universe is not like that. It is lumpy. Gravity is real. And wherever mass concentrations exist, they pull on their surroundings. Every galaxy, every cluster, every supercluster exerts a gravitational tug on its neighbors. This means that every galaxy in the universe has two components to its motion: the smooth recession driven by cosmic expansion, and what astronomers call peculiar velocity, the additional movement caused by the gravitational influence of local structures. For most galaxies, peculiar velocities are relatively modest. The Milky Way's peculiar velocity, for instance, sits at roughly 600 kilometers per second, fast by any everyday standard, but a small perturbation on top of the overall expansion of the universe. What makes peculiar velocities remarkable is what they reveal when you map them systematically across large volumes of space. If you watch the way galaxies deviate from perfect Hubble flow, the idealized recession that pure expansion would produce, you can infer where the mass concentrations are that are pulling them around. It is like watching leaves on the surface of a stream. The overall current carries them downstream, but the eddies and vortices created by rocks and bends reveal the hidden structure of the riverbed. This technique was used to spectacular effect in 2014, when a team of astronomers led by Brent Tully at the University of Hawaii published a landmark paper in Nature. By mapping the peculiar velocities of galaxies across an enormous volume of space, they traced the boundaries of what they called a supercluster, a region within which all galaxy motions are directed inward toward a common gravitational center. This structure spans roughly 500 million light-years and contains approximately 100,000 substantial galaxies, including our own Milky Way, the Andromeda Galaxy, the Virgo cluster, and everything associated with them. They named it Laniakea, from the Hawaiian words for immense heaven. The Laniakea supercluster is not gravitationally bound. It will not survive as a coherent structure in the long run. The expansion of the universe is already pulling its outermost parts away from the center, faster than gravity can hold them. But within it, and especially in its inner regions, gravity is winning the local tug of war, and galaxies are flowing. They are flowing toward a region that astronomers call the Great Attractor. The Great Attractor is one of the most evocatively named objects in astronomy, and in some ways one of the most frustrating. It sits roughly 150 to 250 million light-years away from Earth, in the direction of the Centaurus constellation, except that from our vantage point, it lies almost perfectly behind the densest part of the Milky Way's disk. Dust, gas, and billions of stars in our own galaxy block the view in visible light, creating what astronomers call the zone of avoidance. A band across the sky where extragalactic astronomy becomes extremely difficult. For decades after its existence was inferred from galaxy motions, the Great Attractor itself could not be directly observed. The inference came before the observation. In the late 1970s and 1980s, surveys of galaxy velocities kept turning up the same anomaly. Galaxies in a huge swath of sky, covering hundreds of millions of light years in every direction, were moving in a coordinated way that could not be explained by local structures alone. Something massive and gravitationally powerful was pulling on them, and it was in a direction that was partially hidden. Estimates of its mass eventually converged on roughly 10 quadrillion solar masses, 10,000 trillion times the mass of the Sun, concentrated in a region centered on what is now known to be a rich nest of galaxy clusters, including the Norma cluster. When X-ray astronomy advanced far enough to see through some of the obscuring dust, and when radio surveys filled in other gaps, astronomers got a clearer picture. The Great Attractor is not a single object. It is a region of exceptionally high matter density, a convergence point in the cosmic web, where galaxy clusters and their associated dark matter halos pile up at the intersection of filaments. The Milky Way and everything in Laniakea are flowing towards this region at a steady pace, and have been for billions of years. But here is where the story gets more complicated. The Great Attractor is itself not stationary. It too is being pulled. And the thing pulling it is even more massive, lying further away, and even harder to study. In the 1980s, a group of astronomers known informally as the Seven Samurai found evidence that the entire local supercluster was moving at around 600 kilometers per second toward a point in space well beyond the Great Attractor. This pulled attention toward the Shapley supercluster, a vast concentration of galaxy clusters about 650 million light-years away in the direction of Centaurus. The Shapley concentration is one of the most massive structures in the nearby universe, a supercluster of superclusters, containing clusters with dozens of times the mass of the Virgo cluster. And its gravitational influence reaches far enough to affect galaxy motions across a significant fraction of the observable universe. Even more recently, a 2017 study identified a complementary structure that had been missed for decades. Not an attractor, but a repeller. Dubbed the dipole repeller, this enormous void region lies in roughly the opposite direction from the Shapley concentration, and its emptiness creates an effective push. In the flow patterns of galaxies, Voids are not passive. A region with less matter than average pulls less, and so galaxies on its edges drift away toward denser regions. The dipole repeller, centered near the constellation Leo, appears to be contributing almost as much to the Milky Way's peculiar velocity as the Shapley concentration is attracting it. We are being pulled and pushed simultaneously, running from emptiness toward mass. And we have been the entire time. Zoom out far enough, and the universe stops looking like a collection of individual objects. It reveals itself as a structure, vast, intricate, and deeply organized. Astronomers call it the cosmic web, and once you have seen it, it is impossible to unsee. Matter is not distributed uniformly across space. Instead, it is concentrated into thin filaments, sheets, and nodes, separated by enormous voids that contain almost nothing. When simulated on computers or mapped in real galaxy surveys, the result looks uncannily like a biological neural network, or the structure of foam, or a spider's web strung across the universe at scales that beg a description. The origin of this structure lies in the Big Bang itself, specifically in quantum fluctuations that existed in the first fractions of a second. The universe at its birth was not perfectly smooth. There were microscopic variations in density, tiny regions that were slightly hotter or slightly cooler than the average. These variations were stretched to cosmic scales by inflation, a period of extraordinarily rapid expansion that is thought to have occurred in the universe's first 10 to the power of minus 32 seconds. After inflation, these density variations became the seeds of everything. Regions that were slightly denser than average had slightly stronger gravity, pulling in more matter. That matter increased the density further, attracting more. The process is called gravitational collapse, and over billions of years it sculpted the smooth early universe into the web-like architecture we see today. The filaments that make up the cosmic web are highways of matter. Gas and dark matter flow along them, feeding the rich galaxy clusters that form at their intersections. The largest of these filaments span hundreds of millions of light years, some close to 1 billion, making them among the most extended structures in the observable universe. The Laniakea supercluster sits within such a web, connected by filaments to the Perseus-Pisces chain, a long ridge of galaxies stretching for nearly 1 billion light years, and separated from adjacent structures by voids that are genuinely almost empty. The voids themselves are not nothing. They are filled with the most tenuous imaginable gas, threaded by tiny dark matter filaments, and studded here and there with the most isolated galaxies in the universe. Objects that formed in the cosmic equivalent of the middle of nowhere, and have spent billions of years drifting through near emptiness. Void galaxies tend to be small, blue, and gas-rich, still forming stars at a gentle rate because there is nothing nearby to strip their gas away or disturb their orbits. They are among the simplest galaxies in existence, largely unmolested by the gravitational dramas that shape everything in denser environments. One of the most striking features of the cosmic web is how precisely simulations can reproduce it. Running the laws of physics forward from the initial conditions of the early universe, seeded with the density fluctuations observed in the cosmic microwave background, produces a web that matches observations with impressive fidelity. This is one of the great triumphs of modern cosmology. The structure of the universe on the larger scales is, in broad strokes, understood. What is not fully understood is what has been driving its evolution over the last several billion years and why that evolution has been accelerating. For most of the 20th century, cosmologists assumed that the expansion of the universe was slowing down. The logic was straightforward. Gravity is attractive. All the mass in the universe should be pulling on all the other mass, applying a brake to the outward momentum imparted by the Big Bang. The question was not whether the expansion was decelerating, but by how much, and whether it was decelerating fast enough that the universe would eventually reverse, collapsing back inward in what was called the Big Crunch. To measure the deceleration, you needed to compare the expansion rate at different epochs in the universe's history. The tool for this was the Type 1a supernova. These stellar explosions occur when a white dwarf, which is the dense remnant of a dead star, accumulates enough mass from a companion to trigger a runaway thermonuclear reaction. The result is a cataclysmic explosion so bright it can outshine its entire host galaxy for weeks. What makes Type 1a supernovae scientifically invaluable is that they are standardizable candles. With some calibration for their light curve behavior, their intrinsic brightness can be determined. That means their apparent brightness tells you how far away they are. Combine distance with redshift, and you have a measurement of the expansion rate at the time the supernova exploded. In the late 1990s, two independent teams, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, set out to use distant Type 1 supernovae to measure the deceleration. Both groups expected to find it. Instead, they found the opposite. The supernovae were farther away than they should be if the expansion were slowing. The only explanation that fit the data was that the expansion was not slowing at all. It was speeding up. This result was so unexpected that both teams spent considerable time looking for errors before publishing. It was not what anyone had predicted. It contradicted the most straightforward reading of gravitational physics. It implied the existence of something, some form of energy or pressure or field that was acting against gravity on cosmic scales, pushing the universe apart rather than letting it coast. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for the discovery. The unknown substance driving the acceleration was given a name, dark energy, and the name was chosen deliberately to convey that this was not a minor puzzle. It was a fundamental mystery. To understand why the discovery was so jarring, it helps to consider what was expected. The dominant cosmological debates of the 1990s were about how much matter existed, and whether its gravitational pull was sufficient to stop the expansion. Many cosmologists expected a universe dense enough to eventually recollapse, the Big Crunch scenario. Others expected a universe that would expand forever, but do so at a declining rate, like a ball thrown upward that slows, but never quite stops. The idea that the universe might be accelerating, that the cosmic expansion was not decelerating at all, but actively speeding up, was not seriously on the table. When the supernova data came in, the reaction in the cosmological community was not immediate acceptance. There were serious discussions about whether dust along the line of sight could be dimming the supernovae. whether there were systematic errors in the light curve calibrations, whether the early universe might contain a population of intrinsically dimmer supernovae that could create the illusion of excess distance. Every alternative was studied carefully, and every alternative failed to explain the data as cleanly as the accelerating expansion. By the early 2000s, the community had largely converged on the conclusion that dark energy was real, and that its discovery represented one of the most significant overturns of theoretical expectation in the history of physics. Dark energy is, in one sense, very well characterized. We know roughly how much of it there is. About 68% of the total mass energy content of the universe. We know that its density is extraordinarily low by local standards, approximately 10 to the power of minus 29 grams per cubic centimeter, roughly equivalent to the mass of a few hydrogen atoms spread across a volume the size of a refrigerator. We know that it is essentially uniform across space. It does not clump, it does not concentrate in dense regions, it permeates the cosmos evenly. And we know that its effect is to drive the accelerating expansion that the supernova teams discovered. In the simplest mathematical description, dark energy is represented in Einstein's equations by the cosmological constant, the same term Einstein introduced and then abandoned. It turns out he was right to include it, though wrong about its value. But in another sense, dark energy is almost completely mysterious. No one has ever directly detected it. No experiment has identified the particle or field responsible for it. No one knows why it has the value it does. And the question of what dark energy actually is, physically, fundamentally, remains wide open. The leading candidate is the energy of empty space itself. Quantum mechanics predicts that the vacuum is not truly empty. It seethes with virtual particles, pairs of particles and antiparticles constantly appearing and annihilating. And this quantum activity should contribute an energy density to empty space. When physicists calculate what this vacuum energy density should be, they get a number. When they compare it to the observed value of the cosmological constant, they find a mismatch of somewhere between 60 and 120 orders of magnitude. This discrepancy, sometimes called the worst prediction in the history of physics, suggests that something is deeply wrong with our understanding, either of quantum mechanics, or of gravity, or of the vacuum, or of some combination of all three. The alternative class of explanations involves what are called dynamical dark energy models. Instead of a constant energy density built into the structure of space, these models propose that dark energy is produced by some physical field, typically a scalar field, similar to the Higgs field, whose density and behavior can evolve over cosmic time. Such fields have various names in the literature: quintessence, phantom energy, K-essence. They all share the feature that the effective equation of state, the ratio of pressure to energy density, is not exactly -1, which is what a true cosmological constant would give, but varies. If it varies with time, dark energy in the past was different from dark energy today, and dark energy in the future will be different again. For most of the period since 1998, observations have been consistent with the cosmological constant interpretation. The equation of state has appeared to hover around -1, with error bars too large to definitively rule out variation. Then, in 2024, a new instrument changed the picture. The dark energy spectroscopic instrument known as DESI sits atop the 4-meter Mail telescope at Kitt Peak National Observatory in Arizona. It is equipped with 5,000 robotic fiber optic positioners, each capable of targeting a different galaxy, allowing it to measure the spectra and therefore the redshifts of 5,000 galaxies simultaneously. In its first year of operation, it built a 3-dimensional map of the universe containing tens of millions of galaxy positions. By 2025, it had extended that map substantially and published its second data release. The technique DESI uses to measure cosmic expansion is called baryon acoustic oscillations, or BAO. In the early universe, before atoms could form, the cosmos was a hot, dense plasma, and sound waves propagated through it the way pressure waves move through any medium. These waves established a preferred scale, a characteristic distance at which the density of matter had a slight statistical excess. That was frozen into the distribution of galaxies when the universe cooled enough for hydrogen atoms to form, about 380,000 years after the Big Bang. This frozen pattern, with a characteristic size of about 490 million light-years, acts as the standard ruler. By measuring how large this ruler appears at different redshifts or different epochs in cosmic history, astronomers can track how the expansion rate has changed over time. When DESI's first-year results came out in 2024, they contained a hint of something surprising. Evidence that dark energy's equation of state might not be constant. When the BAO measurements were combined with data from the cosmic microwave background and from Type 1a supernova surveys, the best fit model was not a simple cosmological constant. Instead, it suggested that dark energy might have been stronger, more negative in its equation of state in the distant past, and has been weakening over time. The 2025 DESI results, drawing on 3 years of data, strengthen this hint. Combining BAO measurements with CMB data from the Planck satellite and the Atacama Cosmology Telescope, as well as supernova data from multiple surveys, DESI found a preference for dynamical dark energy at a confidence level of roughly 3 to 4 sigma. Not yet the 5 sigma threshold conventionally required to claim a discovery, but substantial enough to be taken seriously. The preferred model shows an equation of state parameter that was significantly more negative than -1 in the early universe, transitioning to a value closer to -0.8 today. This behavior of dark energy weakening over time is profoundly different from a cosmological constant, and if confirmed, it would constitute one of the most significant discoveries in the history of cosmology. The implications cascade in every direction. A dynamical dark energy that is weakening might eventually stop pushing altogether, or it might strengthen again, or it might reverse sign and become attractive. Without knowing the underlying physics, the future behavior of dark energy is not predictable, which means the long-term fate of the universe, which depends critically on what dark energy does, is genuinely uncertain in a new way. Cosmologist Katie Mack, writing in National Geographic in 2025, put it plainly: if dark energy is dynamical rather than constant, then the confident timeline of the universe's future that cosmologists had been working with for 2 decades has to be reconsidered from the ground up. While the DESI results were reshaping thinking about dark energy, a separate crisis had been deepening for years on a related front. It involves the Hubble constant, the number that describes the current expansion rate of the universe, and the fact that two different methods of measuring it give stubbornly different answers. The first method works in the early universe. The cosmic microwave background, the faint glow of thermal radiation left over from 380,000 years after the Big Bang, contains an extraordinarily detailed record of the early cosmos. Its temperature fluctuations encode information about the composition of the universe, its geometry, and the parameters governing its expansion. By fitting models to these fluctuations, cosmologists can extract a precise value of the Hubble constant. The Planck satellite's measurements give a value of approximately 67 kilometers per second per megaparsec. The second method works in the nearby late-time universe. It uses a chain of distance measurements called the cosmic distance ladder. At the bottom rung are Cepheid variable stars, whose pulsation period is tightly correlated with their intrinsic luminosity, allowing distance to be inferred from brightness. These are used to calibrate the distances to nearby galaxies. Those galaxies in turn host Type 1a supernovae, which can then be seen at far greater distances and used to trace the expansion rate directly. The SH0ES collaboration, led by Adam Rees, uses this method and consistently gets a value of approximately 73 kilometers per second per megaparsec. The discrepancy, roughly 67 versus 73, a gap of about 8 to 9%, is far larger than either measurement's uncertainty. As of late 2025, the tension had exceeded 6 sigma in some analyses. This is the kind of discrepancy that in particle physics would trigger urgent searches for new phenomena. In cosmology, it has been doing exactly that. The James Webb Space Telescope was expected to resolve the tension by providing sharper measurements of Cepheid stars and more precise calibrations of the distance ladder. Instead, it confirmed the Cepheid measurements. The high local value of the Hubble constant was not a product of measurement error in the Cepheid observations. Whatever is causing the discrepancy lies elsewhere. The possibilities are numerous and include modifications to physics in the early universe. For example, a brief period of additional energy density just before recombination, which would shift the sound horizon used in CMB measurements. Modifications to gravity on large scales, dark matter that behaves in unexpected ways, new neutrino physics, or some combination of factors not yet identified. A project called RED-H0T, funded by the European Research Council, is specifically devoted to stress testing every step of both measurement chains, looking for systematic errors that might have been missed. The Euclid Space Telescope, launched in 2023, is providing an independent map of the universe's structure that will eventually offer a third perspective on the tension. What makes the Hubble tension so significant is that both measurement methods are, by this point, extremely well tested. They are not naive or simplistic. They have been checked and rechecked, subjected to years of scrutiny, and updated with better instruments. The most likely explanation is not that someone made an arithmetic error. It is that the standard cosmological model, lambda CDM, which describes a universe containing ordinary matter, cold dark matter, and a cosmological constant, is missing something. The universe is telling us that our best theory of it has a gap, and we have not yet figured out where the gap is or how to fill it. Before going any further into what is moving and where, it is worth understanding how we know any of this. The universe is not the kind of place where you can set up a measuring tape. The tools astronomers use to map motion across cosmic distances are indirect, ingenious, and deeply interconnected, each calibrated against the others in a chain of inference that took most of the 20th century to build. The most fundamental tool is the spectrum of light. When an object is moving toward you, the light it emits is compressed, its wavelengths are shortened, shifted toward the blue end of the visible spectrum. When an object is moving away, the light is stretched, shifting toward the red. This is the Doppler effect applied to light, and it allows astronomers to measure the radial velocity, the speed along the line of sight, of any object that produces identifiable spectral features. Atoms and molecules emit and absorb light at specific wavelengths that function like fingerprints. If those fingerprints appear at shifted wavelengths in a distant object's spectrum, the shift tells you exactly how fast the object is moving, relative to you, and in which direction. For nearby stars and for many galaxies, this technique works beautifully. But interpreting the redshift of very distant galaxies requires care, because there are two different physical processes that can redshift light, and they need to be distinguished. Ordinary Doppler redshift arises from an object moving through space. Cosmological redshift arises from the expansion of space itself, the stretching of the fabric of the universe during the time light was traveling. For galaxies billions of light years away, the dominant contribution to redshift is cosmological, and its interpretation requires a cosmological model. This is part of why measuring the Hubble constant precisely is so important and so difficult. The model you assume when converting redshifts to distances affects the result you get. To measure distances independently of redshift, astronomers rely on standard candles, objects whose intrinsic brightness is known. If you know how bright something actually is, then measuring how bright it appears tells you how far away it is, by the same principle that a streetlight looks dimmer the farther you are from it. The problem is that most objects in the universe don't come with labels announcing their intrinsic brightness. Finding objects whose brightness can be reliably determined requires identifying physical properties that correlate tightly with luminosity. Cepheid variable stars are one such object. These are stars that pulsate regularly, expanding and contracting, with periods ranging from a few days to a few months. Henrietta Swan Leavitt, working at the Harvard Observatory in the early 1900s, discovered that the period of pulsation correlates tightly with the average luminosity. Brighter Cepheids pulsate more slowly, fainter ones more quickly. This relationship, once calibrated with nearby Cepheids, whose distances could be measured by geometric parallax, allows the distance to any galaxy containing Cepheids to be determined. The catch is that Cepheids can only be resolved individually in relatively nearby galaxies, out to a few tens of millions of light years with the Hubble Space Telescope, and somewhat farther with JWST. For distances beyond that range, astronomers step up to Type 1a supernovae, which, as described earlier, serve as standardizable candles that can be seen across billions of light years. But even Type 1a supernovae require calibration. Their peak brightness is not perfectly uniform and must be corrected using the shape of their light curve. And the corrections themselves require calibration against objects at known distances. This chain, parallax to Cepheids to supernovae, is the cosmic distance ladder, and its strength is only as good as each rung's calibration. Beyond supernovae, at truly cosmological distances, additional methods become necessary. Baryon acoustic oscillations, as described in the context of DESI, provide a standard ruler rather than a standard candle. The cosmic microwave background provides a snapshot of the universe at a known epoch that can be used to calibrate models of the expansion. Gravitational lensing, the bending of light by massive objects, can be used to measure the mass of galaxy clusters and to map the distribution of dark matter. Strong lensing systems, where a distant source is multiply-imaged by an intervening mass, can, in principle, give independent Hubble constant measurements through the time delays between the images, a method called time delay cosmography. All of these methods are being actively pursued, refined, and cross-checked. The current situation is that different methods agree remarkably well on many aspects of the cosmological model. The composition of the universe, the geometry of space, the amplitude of density fluctuations, but disagree specifically on the current expansion rate. That disagreement is the Hubble tension, and resolving it requires either finding a systematic error in one or more of the measurement chains, or finding new physics that changes the relationship between early universe observations and late universe measurements. Sitting behind all the visible motion in the universe, behind the flows of galaxies toward attractors, behind the cosmic web of filaments and voids, behind the formation of clusters and superclusters, is an invisible scaffold, dark matter, which makes up roughly 27% of the universe's total mass energy content compared to ordinary matter's 5%. Neither emits nor reflects light. It interacts with ordinary matter only through gravity. Yet, it is responsible, more than anything else, for the structure of the universe as we see it. The first compelling evidence for dark matter came in the 1970s when Vera Rubin and Kent Ford at the Carnegie Institution measured the rotation curves of spiral galaxies, the speeds at which stars orbit around the galactic center at different distances. According to Newtonian mechanics and the distribution of visible mass, stars at the outer edges of a galaxy should be orbiting more slowly than stars near the center, following the same principle that makes the outer planets of the solar system slower than the inner ones. Instead, Rubin and Ford found that rotation velocities were roughly constant from the inner regions all the way to the outermost stars they could measure. The galaxies were rotating as though they contained far more mass than was visible. Mass distributed in a large, roughly spherical halo extending well beyond the visible disk. This discovery has been confirmed countless times by countless independent methods. Gravitational lensing reveals mass in galaxy clusters that exceeds the visible mass by factors of 5 or more. The temperature of hot gas in galaxy clusters, traceable by X-ray telescopes, reflects the gravitational potential well the gas sits in, and that potential well is far deeper than the visible mass alone could create. The cosmic microwave background's fluctuation pattern encodes the ratio of ordinary matter to total matter, and the fit requires dark matter. Simulations of structure formation reproduce the observed cosmic web only when dark matter is included, providing the dominant gravitational scaffold that ordinary matter falls into. What dark matter does in the context of cosmic motion is provide the seeds and the framework for everything. In the early universe, ordinary matter was coupled to photons in the hot plasma, unable to collapse under its own gravity because the radiation pressure kept pushing it back. Dark matter, which does not interact with photons, was not subject to this pressure and could begin collapsing much earlier, building gravitational potential wells. When ordinary matter eventually decoupled from the radiation at the epoch of recombination, 380,000 years after the Big Bang, it fell into the wells that dark matter had already prepared. Stars and galaxies formed in those wells. Galaxy clusters formed at the deepest wells. Filaments traced the bridges between wells. The large-scale flows of galaxies, the peculiar velocities that allow astronomers to map Laniakea and identify the Great Attractor, are, fundamentally, the infall of ordinary matter into structures defined by dark matter. Every galaxy moving towards the Shapley concentration is following a gradient in the dark matter gravitational field. Every void is a place where dark matter density was slightly below average in the early universe, and ordinary matter has been draining away from it ever since, leaving the void progressively emptier. Dark matter halos also govern the fate of individual galaxies during mergers. When the Milky Way and Andromeda interact, in whichever scenario plays out over the coming billions of years, the first effects will be felt in their extended dark matter halos, which are far larger than the visible galaxies they surround. The halos of the two galaxies are already overlapping at their current separation of 2.5 million light-years. Dynamical friction between the halos is already slowly extracting energy from the relative motion of the two galaxies, gradually drawing them closer, a process that has been operating for billions of years and will continue to do so regardless of what the visible stellar disks do. Despite its foundational importance, dark matter remains unidentified at the particle level. Decades of direct detection experiments, underground detectors designed to catch dark matter particles scattering off ordinary nuclei, have produced no confirmed detections. Collider experiments at the Large Hadron Collider at CERN have not produced any particle consistent with the most popular dark matter candidates. Indirect detection searches looking for gamma rays or other signals produced when dark matter particles annihilate each other in dense regions have also come up empty. The leading candidates, weakly interacting massive particles, or WIMPs, were theoretically attractive because of a remarkable coincidence between the mass and interaction strength, predicted by supersymmetric theories and the relic abundance required to explain observations. That coincidence is now strained by the lack of detections. Alternative candidates include axions, sterile neutrinos, primordial black holes, and various more exotic proposals. None has been confirmed. All the drama of dark energy and cosmic expansion plays out on scales of hundreds of millions to billions of light years. Much closer to home, on the scale of the few million light years that make up our local group of galaxies, gravity is still firmly in charge, and the motions are different in character, more intimate, more chaotic, and more consequential for the long-term future of our own galaxy. The local group contains more than 80 known galaxies, most of them small dwarf galaxies orbiting as satellites around the two heavyweights, the Milky Way and the Andromeda Galaxy, known to astronomers as M31. These two galaxies are roughly 2.5 million light-years apart, so close that Andromeda is, in fact, the most distant object visible to the naked eye from Earth, and they are moving toward each other. For decades after this was established, astronomers treated the eventual collision between the Milky Way and Andromeda as a near certainty. The 2012 Hubble Space Telescope measurements of Andromeda's motion concluded that a major collision was essentially guaranteed, with a first closed passage expected in about 3.9 billion years, and a full merger into a new, larger galaxy informally named Milkomeda, expected to be complete within about 6 to 10 billion years from now. The resulting object was expected to be a giant elliptical galaxy, featureless compared to the elegant spirals that produced it, with the two central, supermassive black holes eventually spiraling together and merging over a span of millions of years after the galaxy cores had combined. But a 2025 study published in Nature Astronomy complicated this picture substantially. A team led by Till Sawala at the University of Helsinki incorporated data from both the Gaia spacecraft and the Hubble Space Telescope, much more precise measurements of Andromeda's motion than were available in 2012, and factored in something the earlier simulations had treated simplistically: the gravitational influence of the other large members of the local group, especially the Large Magellanic Cloud and the Triangulum Galaxy. Running 100,000 simulations of the local group's future with these additional bodies included, the team found that the probability of a Milky Way Andromeda collision within the next 10 billion years is only about 50%. The Large Magellanic Cloud, which has a mass roughly 15% of the Milky Way's, turns out to matter. Its orbit carries it perpendicular to the Andromeda Milky Way approach trajectory, exerting a gravitational tug that can deflect the Milky Way's path enough, in some simulations, to prevent a close encounter with Andromeda entirely. In the simulations where the galaxies do pass close enough to merge, the process unfolds roughly as previously envisioned. Multiple passes, each one draining energy from the orbit through dynamical friction, gas compression triggering intense bursts of star formation, and eventual settling into a larger, rounder system. In the simulations where they miss each other, the galaxies continue evolving separately, eventually losing all other galaxies beyond their gravitationally bound local neighborhood as the expanding universe carries everything else away. The Sun's fate during the merger, in the scenarios where it occurs, is less dramatic than might be imagined. Stars are so far apart, even in the densest parts of a galaxy, that actual stellar collisions are essentially impossible. The Sun would not be hit. It might, however, be gravitationally scattered into a new orbit, possibly much further from the combined galaxy's center than its current position. The night sky, as seen from a hypothetical observer on Earth at that time, would be spectacular. Andromeda growing to fill a large arc of sky in the final approach, eventually breaking apart into streams of stars as the two disks interpenetrate. But the Earth will almost certainly be uninhabitable by then anyway. Scorched by the sun's gradual increase in luminosity over billions of years, long before the collision occurs in those scenarios where it happens. While the Milky Way and Andromeda play out their uncertain dance, and while the Great Attractor draws the contents of Laniakea toward its center, and while dark energy pushes the universe apart at accelerating rates, gravity is busy at every scale simultaneously. The interplay between these forces, between local attraction and cosmic expansion, determines which structures survive and which are pulled apart. The boundary between survival and dissolution is set by something called the local Hubble flow. Inside a region where gravity is strong enough to overcome the expansion, where the gravitational escape velocity exceeds the rate at which space is being pulled apart, structures can remain bound. Outside that region, expansion wins. The Milky Way and Andromeda are close enough and massive enough that they are bound to each other, even in the scenarios where they do not merge within the next 10 billion years. The local group as a whole, our galaxy, Andromeda, the Triangulum galaxy, and the dozens of dwarf satellites orbiting them, is gravitationally bound and will persist as a coherent structure essentially indefinitely, even as the universe around it continues to expand. On slightly larger scales, some galaxy clusters are similarly bound. The Virgo cluster, the nearest large cluster to the Milky Way at about 54 million light-years away, contains roughly 1,300 known galaxies and has sufficient mass to keep them gravitationally associated. The Fornax cluster, Perseus cluster, Coma cluster, and similar structures are all gravitationally bound systems that will survive the cosmic expansion. Within each cluster, galaxies continue to orbit, interact, merge, and evolve, playing out their own internal dramas over billions of years. The masses involved in these bound systems are immense. The Coma cluster, one of the most massive clusters in the nearby universe at about 330 million light-years away, contains over 1,000 catalogued galaxies and has a total mass roughly 1,000 times that of the Milky Way. Most of it in the form of hot X-ray emitting gas and dark matter. The hot intracluster medium, plasma at temperatures of tens of millions of degrees, far hotter than the surface of most stars, fills the space between the cluster galaxies, radiating in X-rays. This gas is so hot because it has been shock heated by infalling material over billions of years, continuously fed as new galaxies fell into the cluster and had their cold gas stripped away. The intracluster medium is itself one of the largest reservoirs of ordinary matter in the universe, containing more baryons than all the stars in the cluster galaxies combined. What will not survive are the larger scale structures, the superclusters. Laniakea itself is already in the process of being torn apart. Its outermost galaxies are already receding faster than the Great Attractor can pull them back. The Shapley concentration, whose gravitational influence we feel at a distance of 650 million light-years, is pulling on us but cannot prevent the space between us and it from continuing to grow. Eventually, the expansion will overwhelm the gravitational signal from even the most massive structures, and the observable universe will become increasingly lonely. Reduced to isolated island universes, each gravitationally bound island separated from all others by distances that cannot be crossed. This is happening at a pace that is invisible on human timescales, but real. The universe that existed 13.8 billion years ago was younger, denser, and more richly connected than the one we inhabit now. The universe that will exist 100 billion years from now will be darker, emptier, and far more isolated than the present one. The direction of cosmic time is, on the larger scales, toward increasing desolation. Understanding the current balance between gravity and expansion also reveals something important about why life exists at all. If dark energy had been stronger in the past, if it had come to dominate the energy budget of the universe before gravity could assemble galaxies, stars, and planetary systems, then none of the structures we observe, including ourselves, would have had time to form. The fact that dark energy waited roughly 5 to 7 billion years to begin dominating, allowing gravity to build the cosmic web and assemble trillions of stars in hundreds of billions of galaxies, is either a striking coincidence or evidence of some deep principle we do not yet understand. The theoretical puzzle of why the cosmological constant has the specific, small, positive value it does, rather than being zero or enormously larger, is called the cosmological constant problem, and it remains one of the most significant open questions in all of theoretical physics. There is a concept in cosmology that carries an uncomfortable implication. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is not the same as the entire universe, and it is not fixed. As time passes and the expansion continues, more distant regions that are currently beyond the horizon may, in some circumstances, come within reach. But because the expansion is accelerating, the reverse is also true. Light emitted today from galaxies beyond a certain distance, called the cosmic event horizon, will never reach us. The universe is not merely large, it is becoming effectively smaller in the sense that the number of galaxies accessible to observation is decreasing over time. The current cosmic event horizon sits at roughly 16 billion light years. Any galaxy that is currently beyond that distance and receding faster than light, which is allowed because it is space itself that is expanding, not objects moving through space, will never be able to send us a signal that we can receive, no matter how long we wait. This is not a speed limit in the ordinary sense. It is a consequence of the geometry of an accelerating universe. The practical consequence is that the visible universe is shrinking in terms of accessible galaxies. Right now, we can observe roughly 2 trillion galaxies within the observable universe. Over the next 100 billion years or so, as the expansion continues to accelerate and more galaxies cross the event horizon, that number will drop dramatically. The galaxies in our local group will remain visible. They are gravitationally bound to us, not receding with the expansion. But virtually everything beyond the local group will eventually become unreachable and, eventually, unobservable. Their light will be stretched to such extreme redshifts that it falls below any detectable threshold. Future observers, if there are any, will inherit a universe that looks qualitatively different from the one we see. They will observe a local group that has merged into a single structure, surrounded by darkness. They will have no way, from observation alone, to know that the universe was once filled with 2 trillion galaxies. the cosmic microwave background will have redshifted beyond detectability. The standard candles used to discover dark energy will have drifted beyond the horizon. If the expansion continues as currently understood, those future observers will look out and see a universe that appears, from their vantage point, to be static and eternal. A single, lonely galaxy surrounded by empty space. All the evidence that once pointed to a hot Big Bang and an expanding cosmos will have been erased. This is not a distant science fiction scenario. The timeline for the most accessible galaxies to cross the event horizon is measured in tens of billions of years. A long time for a human, an eye blink for a cosmologist. The crisis in cosmology created by the Hubble tension and the hints from DESI about dynamical dark energy have triggered a surge of new instruments and methods designed to constrain the expansion of the universe with greater precision and independence. The goal is to build enough independent lines of evidence that the true source of the discrepancy becomes identifiable, rather than hidden behind any single technique's assumptions. Gravitational waves offer one of the most promising new tools. When two neutron stars merge, or two black holes, or a neutron star and a black hole, the event radiates gravitational waves, ripples in space-time that propagate at the speed of light. By measuring the amplitude and frequency evolution of these gravitational waves, physicists can calculate the intrinsic brightness of the merger, how much energy it released, without relying on any calibration chain involving Cepheid stars or supernovae. Combining this with the redshift of the host galaxy gives an independent measurement of the Hubble constant. This method, proposed by Bernard Schutz in 1986 and first applied to the landmark neutron star merger GW170817 in 2017, is called the Standard Siren method. It currently has large uncertainties because only a handful of events have been observed and identified with host galaxies. But as gravitational wave detectors become more sensitive and more mergers are observed, the precision will improve significantly. The Euclid Space Telescope, launched by the European Space Agency in 2023, is conducting one of the largest galaxy surveys ever undertaken. Its primary mission is to map the large-scale structure of the universe, the distribution of hundreds of millions of galaxies, across a significant fraction of cosmic history. By tracking baryon acoustic oscillations across this huge sample, Euclid will provide constraints on the expansion history of the universe that are independent of both the CMB and the local distance ladder. Its results, expected to arrive in stages over the coming years, may help determine whether the Hubble tension points to a problem with early universe physics, late universe physics, or both. The Nancy Grace Roman Space Telescope, named for the astronomer often called the Mother of Hubble, is designed to observe Type 1a supernovae at unprecedented precision and volume, with a field of view 100 times larger than Hubble's. While maintaining the same angular resolution, Roman will be able to survey supernovae across a much wider range of redshifts, tightening the constraints on the equation of state of dark energy and providing an independent check on the local Hubble constant. And on the ground, the Vera C. Rubin Observatory, named for the astronomer who provided the strongest early evidence for dark matter, has begun its legacy survey of space and time, a 10-year program expected to image tens of billions of objects in 6 different wavelength bands, discovering millions of supernovae, mapping weak gravitational lensing across large fractions of the sky, and contributing to virtually every area of cosmological measurement. The combination of Euclid, Roman, and Rubin is expected to usher in what some cosmologists call a golden age of cosmology, a period in which measurements become precise enough to definitively settle the Hubble tension, and either confirm or refute the hints from DESI. While cosmic expansion is gradually dismantling the connections between galaxy clusters and superclusters, inside the gravitationally bound structures, the clusters, the groups, the local group, a completely different process is unfolding. Gravity continues to operate undisturbed, and the long-term future of bound systems is dominated by mergers, cannibalism, and the slow exhaustion of the fuel that makes stars possible. Galaxy mergers are not rare events. They are, in fact, one of the primary mechanisms by which large galaxies have grown to their current sizes. The Milky Way itself has a history of mergers, most recently with the Gaia Sausage Enceladus galaxy, a system of similar mass that crashed into the proto-Milky Way roughly 8 to 10 billion years ago, contributing tens of billions of stars that are now recognizable in the galactic halo by their distinctive orbits. The Sagittarius dwarf galaxy is currently being tidally disrupted and absorbed by the Milky Way. The Milky Way has a massive tidal tail of stars, stripped from its interactions with the Magellanic Clouds. On the cosmic timescale of a galaxy formation, our galaxy is not a serene, undisturbed spiral. It is an ongoing building project, incorporating smaller systems into its growing mass. In the broader universe, the merger rate has been declining since its peak around 8 to 10 billion years ago, when the universe was younger and denser and galaxy separations were smaller. But inside gravitationally bound clusters, mergers will continue for trillions of years into the future. In a cluster like Virgo, with over 1,300 galaxies in a relatively compact volume, dynamical friction, the same mechanism that governs the approach of the Milky Way and Andromeda, is constantly draining energy from galaxy orbits. Over billions of years, galaxies spiral toward the cluster center, eventually merging with whatever large galaxy sits there. The result, over cosmic time, is that clusters tend to become dominated by a single massive galaxy. A brightest cluster galaxy, or BCG, that has cannibalized its neighbors. These objects are already among the largest galaxies known, with IC1101 as the most extreme example, sitting at the center of the Abell 2029 cluster with a stellar mass approaching 100 trillion solar masses. IC1101 grew to its extraordinary size precisely through this process of repeated cannibalism, absorbing smaller galaxies over billions of years while sitting at the convergence point of multiple filaments that continued feeding it material. This process will continue in the Virgo cluster, the Perseus cluster, the Coma cluster, and every other bound cluster in the universe. Over the next few 100 billion years, each cluster will gradually consolidate its member galaxies into one or a small number of massive systems. The structural diversity we see in clusters today, spirals, ellipticals, lenticulars, dwarfs, will be replaced by relative uniformity, dominated by giant elliptical galaxies that have consumed their environments. Inside those galaxies, a parallel process drives the evolution of stellar populations. The gas that fuels star formation is a finite resource. As it is consumed by successive generations of stars, less and less remains available. Massive stars live and die quickly, enriching the interstellar medium with heavy elements, but also returning some gas and energy. But the net effect, over billions of years, is that the star-forming gas is gradually depleted. When it is gone, the galaxy stops making new stars. The existing stars continue to shine, but they are aging. The most massive, the brightest, bluest stars die first, within millions of years. Then, the intermediate mass stars, over billions of years. What remains as the gas is used up and the bright stars die is an increasingly red, increasingly old stellar population, dominated by faint, long-lived low-mass stars that can persist for tens of billions to over 100 billion years. Galaxies in dense cluster environments lose their gas even faster than isolated galaxies. Stripped by ram pressure as they move through the hot intracluster medium and harassed by gravitational interactions with their neighbors. The process of reddening and quenching, the cessation of a star formation, transforms blue, gas-rich star-forming galaxies into red, gas-poor, passively evolving ones. Most large elliptical galaxies and clusters today are already quenched, their star-forming days long behind them. They are in the process of slow cooling toward the fate that all stars eventually share. The supermassive black holes at the centers of all large galaxies will outlast the stars around them. They grow through accretion of gas and through mergers with other black holes. In the distant future, as galaxies merge and gas is exhausted, the black holes will mostly cease active growth and enter a quiescent phase. Their gravitational influence on the surrounding stellar population continues, however, gradually scattering stars into increasingly wide orbits, occasionally ejecting stars entirely from the galaxy, and very rarely pulling stars close enough to disrupt them in tidal disruption events that briefly resurrect the black hole's brief luminosity. This activity will persist at declining rates across the degenerate era that follows the end of star formation. The gravitational interactions between stars in a galaxy over truly vast timescales also gradually alter the overall structure. In a dense stellar system, exchanges of energy between stars on close approaches slowly result in lighter stars gaining energy and drifting outward, while heavier remnants sink toward the center. This process, called dynamical relaxation, operates on timescales much longer than the current age of the universe for large galaxies, but becomes relevant over the trillions of years of the degenerate era. Eventually, the stellar remnants remaining in a galaxy's outer regions will have so little gravitational binding to the central mass that they drift away, one by one, leaving behind an ever more concentrated core. The timescale for a galaxy to lose half its mass by this process is enormously long, on the order of 10 to the power of 19 to 10 to the power of 20 years. But it is finite. Even the gravitationally bound galaxy clusters of the far future are not truly eternal. One of the most unsettling implications of cosmic acceleration concerns knowledge itself. The universe contains an extraordinary amount of information about its own past, written in the positions of galaxies, the spectra of their light, the temperature fluctuations of the cosmic microwave background. Right now, in 2026, we are living in the richest observational epoch in cosmic history. The universe is old enough that structure has had time to develop and diversify, but young enough that the evidence of the Big Bang is still clearly visible. The cosmic web is still apparent across billions of light years, and the recession of distant galaxies provides a direct window into the universe's expansion history over billions of years. This will not always be the case, as the accelerating expansion carries distant galaxies across the cosmic event horizon. The information they carry goes with them. A galaxy that is today marginally detectable at the edge of our observable universe will, tens of billions of years from now, be completely inaccessible. Its light, stretched by the expansion, will have redshifted to wavelengths so long that no conceivable instrument could detect them. More fundamentally, any new light it emits will never reach us. We are outside each other's event horizons. Consider what this means for a civilization of astronomers living, say, 1 trillion years from now in the Milky galaxy, or whatever the merged remnant of the local group has become. They look out from their galaxy, or what remains of it, and see nothing but darkness. Every galaxy that was not gravitationally bound to the local group at the time of the present era will have long since crossed the horizon. The cosmic microwave background, redshifted from its current average temperature of 2.7 Kelvin by another factor of perhaps 1,000, will be at a temperature of roughly 0.003 Kelvin, so cold that even the best thermometer imaginable would struggle to distinguish it from absolute zero. It will carry no practical information. Those future astronomers would have no observational evidence for the Big Bang. They would have no evidence of the cosmic web, no galaxy redshift surveys to map the expansion of the universe, no Type 1a supernovae at cosmological distances to measure the acceleration. They would see a small number of galaxies, the surviving remnants of the local group's merger, surrounded by apparent emptiness. From pure observation, they would have no way to know that the universe was ever anything other than what they see. The expanding universe would be invisible to them. This is not a hypothetical or a thought experiment. It is the logical consequence of current cosmology, and it was first articulated clearly by cosmologist Lawrence Krauss and collaborator Robert Scherer in a 2007 paper that bears the rather poetic title, The Return of a Static Universe and the End of Cosmology. Their argument was simple but profound. All the observational evidence for the Big Bang, the expansion, and dark energy will eventually disappear. If our descendants do not record this evidence, if the knowledge is not preserved, it will be permanently lost. This raises a peculiar thought. We may, in fact, be living in the only epoch of cosmic history when the questions, where did the universe come from? And where is everything going? Are answerable from observation alone. In the distant past, the universe was too young and hot and dense for structure to be visible. In the distant future, the evidence will be washed out by the expansion. Right now, in this narrow window of cosmic time, the universe has arranged itself to be readable, to offer observers who look carefully enough a nearly complete record of its own past and a visible preview of its own future. That is not a small thing. It is, depending on how you think about it, either a remarkable coincidence or a reason to take cosmology seriously as one of the most time-sensitive scientific enterprises in the universe's history. Everything so far, the cosmic web, the Great Attractor, the expansion, the Hubble constant, the DESI results, feeds into a question that sits at the far end of cosmological thinking. What is the ultimate fate of the universe? The answer depends, more than anything else, on the nature of dark energy. If dark energy is a true cosmological constant, constant in density, constant in its effect, then the universe's fate is what astronomers call the Big Freeze, or heat death. The expansion continues indefinitely, accelerating forever. Galaxies beyond the local group are carried away until they cross the event horizon and vanish from view. Star formation continues for a while, as long as galaxies retain gas, but eventually the raw material is exhausted. Roughly 100 trillion years from now, 10,000 times the current age of the universe, the last new stars will form. After that, the universe enters what Adams and Laughlin called the degenerate era, a vast dark span of time during which the cosmos is populated only by the dim embers of stellar remnants. White dwarfs slowly cool and fade to become black dwarfs, objects so cold and dark they are effectively invisible, radiating nothing. Neutron stars spin down, the universe grows progressively darker. Black holes alone remain as significant objects, persisting through the degenerate era into the black hole era. By around 10 to the power of 40 years from now, all ordinary matter not locked in black holes will have succumbed to proton decay, if protons do decay, which remains experimentally unconfirmed, or been disrupted by the gravitational dynamics of whatever structures remain. Even if protons don't decay, random quantum processes over immense timescales will gradually disintegrate ordinary matter in other ways. Black holes persist because nothing inside their event horizons can escape in any ordinary sense. But Stephen Hawking's theoretical work in the 1970s showed that black holes are not perfectly stable. They emit radiation, now called Hawking radiation, at a rate that depends on their mass. The more massive the black hole, the slower it radiates. Stellar mass black holes will evaporate on timescales of around 10 to the power of 67 years. The supermassive black holes at the centers of galaxies, the monsters with billions of solar masses, take far longer, up to around 10 to the power of 100 years. But they evaporate too. Eventually, even the last black hole radiates away its final particle of energy. After that, the dark era. A universe containing nothing but a thin, dilute gas of photons and elementary particles, spread across a volume so vast that interactions between particles are vanishingly rare. Temperatures approaching absolute zero. No free energy, no gradients, no processes capable of doing work. This is the thermodynamic end state that physicists call equilibrium, maximum entropy, no further evolution possible. The universe does not die in any dramatic sense. It simply runs down, as though the battery that powered it is finally, irreversibly depleted. This is the fate implied by a cosmological constant. But if dark energy is dynamical, if DES Wig's hints harden into confirmed measurements, other endings become possible. If dark energy is strengthening over time rather than remaining constant, the universe's future diverges dramatically from the Big Freeze scenario. The relevant parameter is the equation of state. The ratio of pressure to energy density, typically denoted as W, For a cosmological constant, W equals exactly -1. For dark energy that weakens over time, W is greater than -1. For dark energy that strengthens over time, called phantom energy, W is less than -1. Phantom energy is physically unusual because it has negative kinetic energy, a property that most physical theories struggle to accommodate without producing instabilities. But if it is real, its consequences are profound. An energy density that strengthens as the universe expands means that the expansion itself accelerates in an ever-escalating feedback loop. Unlike a cosmological constant, which drives exponential expansion at a steady rate, phantom energy drives super exponential expansion. The scale factor of the universe grows without limit in a finite amount of time, ending in what is called the Big Rip. The DESI results, taken at face value, are curious in this regard. The best fit model suggests that dark energy behaved more like phantom energy in the distant past, with W significantly below -1, and has been moving toward less negative values over time. If this trend continues, dark energy's behavior will eventually cross the boundary at W equals -1 from the phantom side, settling into something more like quintessence. This would suggest the universe is moving away from the Big Rip scenario rather than toward it. But without understanding the underlying physics, extrapolating the trend into the future is not reliable. The Big Rip scenario, if it occurs, unfolds on a timeline determined by how quickly W deviates from -1 and in what direction. In the original 2003 paper by Robert Caldwell, Mark Kamionkowski, and Natalie Weinberg, which introduced the concept, the Big Rip was estimated to occur roughly 22 billion years from now if W equals -1.5, though the specific timing depends strongly on the exact value of W and its potential evolution. The sequence of events is methodically violent. Galaxy clusters are ripped apart roughly 200 million years before the end. The Milky Way, or whatever has become of it, is disrupted roughly 60 million years before the end. The solar system is gravitationally unbound, about 3 months before the end. The Earth is ripped apart in the final minutes. Atoms are dissociated in the final microseconds. The Big Rip ends in a singularity, not unlike the Big Bang run in reverse. A completely different class of endings involves the possibility that dark energy is not permanent. Some models propose that dark energy is the energy of a quantum field that is currently stuck in a metastable state, what physicists call a false vacuum. If the field were to tunnel quantum mechanically to its true, lower energy state, the result would be vacuum decay. A bubble of new, lower energy vacuum nucleating somewhere in space and expanding at the speed of light, consuming and destroying everything in its path. From inside the approaching bubble, nothing would provide warning. The bubble wall travels at the speed of light. The probability of this occurring at any given moment is essentially zero, but in an infinite universe, it could happen anywhere at any time. This scenario, popularized by the work of Sidney Coleman in the late 1970s, remains speculative. It requires the universe's quantum vacuum to actually be metastable, which is possible but unconfirmed. And then there is the option that some DESI observers have cautiously raised. If dark energy is weakening and eventually reverses sign, becoming attractive rather than repulsive, the expansion could slow, stop, and reverse, leading to a big crunch. The universe would collapse back on itself, growing hotter and denser until it ends in a state resembling the initial singularity of the Big Bang. Some cyclic cosmological models propose that such collapses are followed immediately by new Big Bangs, producing a sequence of universes that expand and contract repeatedly. These models face serious thermodynamic objections. Entropy builds up from cycle to cycle, but have not been ruled out definitively. There is something philosophically striking about the fact that we can answer the question, where is everything going at all? The universe is 13.8 billion years old. Humanity has been doing systematic astronomy for perhaps 5 centuries, and cosmology as a quantitative science is barely 100 years old. In that time, we have gone from believing the universe to be static and eternal to understanding that it began in a hot, dense state, expanded and cooled, structured itself through gravity and quantum fluctuations into a vast cosmic web, and is now being driven apart by a force we cannot identify and cannot directly observe. The motion of everything in the universe is the result of 2 competing impulses. Gravity, the attraction of mass for mass, built into the fabric of space-time by Einstein's equations, pulls things together at every scale from planets to galaxy clusters. It is the sculptor of structure, the force that assembled clouds of hydrogen into stars, stars into galaxies, and galaxies into the web we inhabit. Without gravity, there would be no structure, no complexity, and no observers to notice any of this. Dark energy, whatever it is, pushes in the opposite direction. It is the force that is steadily dismantling the connections between gravitationally bound islands, carrying the universe toward eventual desolation. It won the competition with gravity about 5 to 7 billion years ago, roughly when the sun was forming, and has been winning ever since. Before that transition, the expanding universe was decelerating. Gravity was applying the brake. After it, the brake was released, and the universe has been accelerating into the dark. The peculiar velocities of galaxies, the flows toward the Great Attractor, the pull of the Shapley concentration, the push of the dipole repeller, are the fingerprints of this competition, played out at intermediate scales. They are the map of what gravity has built over 13 billion years, and they will persist for billions more, even as the universe around the structures fades. The Hubble tension and the DESA results are not failures of cosmology. They are its frontier. They represent places where the standard model, extraordinarily successful as it is straining against observational reality, hinting that something is missing. The history of cosmology is a history of surprises. The expanding universe, the cosmic microwave background, dark matter, dark energy, the accelerating expansion, the cosmic web. Every time a new observation challenged the prevailing picture, the picture deepened. There is every reason to think the same will happen again. One of the most precise measurements of cosmic motion available to astronomers comes from an instrument that was not originally designed to measure motion at all. The cosmic microwave background, the faint thermal radiation that permeates the entire sky, a relic of the universe's first 380,000 years, is not perfectly uniform. It has temperature fluctuations at the level of 1 part in 100,000. These fluctuations are the seeds of cosmic structure, imprinted in the early universe and preserved across 13.8 billion years of cosmic evolution. But the microwave background also carries a much larger amplitude pattern that is not about structure at all. It is about motion. When astronomers map the microwave background across the sky, one of the first things they see, before the subtle 1 in 100,000 fluctuations, is a dipole pattern. One side of the sky is very slightly hotter, the opposite side is very slightly cooler, with the temperature difference amounting to about 3.4 millikelvin across the whole sphere. This dipole has a straightforward physical interpretation. The Earth, moving through the sea of microwave photons, Doppler shifts the radiation it is moving toward to slightly higher frequencies, and the radiation it is moving away from to slightly lower frequencies. The dipole tells us our total velocity relative to the rest frame of the microwave background, the frame in which the early universe was, to an excellent approximation, at rest. That velocity is about 370 kilometers per second, pointing toward the constellation Leo. This is the combined effect of all the motions stacked on top of each other. Earth orbiting the Sun at about 30 kilometers per second, the Sun orbiting the galactic center at about 220 kilometers per second, the Milky Way moving within the local group, and the local group being carried by the peculiar velocity of Laniakea toward the Great Attractor and Shapley. Subtracting the known contributions from the solar system and galactic orbits, what remains is the peculiar velocity of the local group, about 627 kilometers per second, directed toward a point in the southern sky, roughly consistent with the direction of the Shapley supercluster after accounting for the opposing push of the dipole repeller. The CMB dipole is in some ways the most honest motion measurement we have. It does not require calibrating a distance ladder, does not require assuming a cosmological model, does not rely on the spectra of individual galaxies. It measures our velocity directly against the closest thing to an absolute rest frame that exists in the observable universe. And it confirms simply and precisely that we are not sitting still. We never were. But the CMB contains an even more ancient record of motion, or rather, of what motion was like in the first fraction of a second of the universe's existence. The tiny fluctuations that eventually became galaxies and the cosmic web were not random noise. They have a specific statistical pattern, a particular spectrum of amplitudes across different angular scales that matches the predictions of cosmic inflation with remarkable precision. Inflation proposes that the universe underwent an extraordinarily rapid, exponential expansion in the first 10 to the power of minus 32 seconds, driven by the energy of a scalar field called the inflaton. During this period, the universe expanded by at least a factor of 10 to the 26th power, possibly far more, in an almost incomprehensibly short time. The motion during inflation was not the motion of objects through space. It was the motion of space itself, expanding so fast that regions that had been in contact, close enough to exchange energy and reach thermal equilibrium, were carried apart before light could travel between them. This solves what cosmologists call the horizon problem. The fact that opposite sides of the observable universe, which were never in causal contact by the time the microwave background was emitted, are at the same temperature to 1 part in 100,000. If they were not in causal contact, how did they reach the same temperature? The answer is they were in causal contact, briefly, before inflation pulled them apart. Inflation also explains the flatness of the universe, the observation that, to high precision, space appears to be neither positively nor negatively curved, but geometrically flat, because any curvature present before inflation would have been stretched away. The quantum fluctuations that inflation stretched to cosmic scales were oscillating in the hot, dense plasma that followed inflation as sound waves. These are the baryon acoustic oscillations that DESI uses as its standard ruler. The same oscillations that encoded a characteristic scale in the distribution of galaxies. The motion of sound through the primordial plasma is, in a direct sense, the physical origin of the patterns we are now using to measure the expansion of the universe billions of years later. The cosmic web has a complement that is as informative as its dense filaments and clusters. The voids. Roughly 80% of the volume of the observable universe is occupied by voids. Regions where the density of matter is far below average, extending from tens of millions to hundreds of millions of light years across. They are not empty in an absolute sense, but they are empty enough that the average galaxy inside a void is far more isolated than a galaxy in a cluster or even a field region. Voids are not passive, they play an active role in the dynamics of the cosmic web. As matter flows out of void interiors along the mild gravitational gradients that direct matter toward filaments and sheets, the voids grow. The walls of voids, the sheets and filaments bounding them, are fed by this drainage, and become the environments where galaxy formation is most vigorous. Void interiors, drained of most of their matter, become progressively emptier over time. This means that the cosmic web is not static, but evolving. Voids grow, merge with neighboring voids, and the walls between them thin. At late times, with dark energy accelerating the expansion, this process is enhanced because the additional expansion suppresses the growth of structure, preventing new filaments from forming and allowing voids to dominate an increasing fraction of the volume. The Boötes void, discovered in 1981, is one of the most famous examples. It spans roughly 330 million light years, and was, at the time of its discovery, so unexpectedly large that some astronomers questioned whether the standard model of structure formation could produce it. The Eridanus supervoid, even larger at about 1 billion light years across, has been suggested as the source of the cold spot, an anomalously cold region in the cosmic microwave background, though the connection remains debated. Voids also provide an independent way to measure dark energy. Because void growth is sensitive to the rate at which structure formation is suppressed, and because dark energy suppresses structure formation by accelerating the expansion, the sizes and profiles of voids carry information about dark energy's equation of state. This is a different kind of measurement from supernovae or BAO. It probes the growth of structure rather than the geometry of the universe, and it complements the other methods. The Euclid survey will produce one of the most comprehensive void catalogues ever assembled, potentially providing constraints on dark energy's behavior that are competitive with those from BAO. Inside the voids, the few galaxies that do exist are among the most scientifically interesting objects in the universe. Void galaxies are typically dwarf or intermediate mass spirals, bluer and more gas-rich than galaxies in denser environments. They form stars at a slow, steady pace, undisturbed by the tidal forces and ram pressure stripping that affect galaxies in clusters. They tend to be less massive than cluster galaxies because they formed in an environment with fewer mergers to drive their growth. Studying them provides a clean look at galaxy evolution in isolation, a control group for understanding how the environment shapes the galaxies that form within it. The motion of void galaxies is particularly instructive. They drift outward from void centers as the expansion drives everything apart, moving away from the denser filaments and walls at the void periphery. This outward flow is not the same as cosmic expansion. It is a local effect driven by the underdensity of the void itself, a kind of reverse infall toward emptiness. Mapping these flows in detail and comparing them to what cosmological simulations predict provides a test of our models of structure formation and dark energy that is complementary to the cluster infall motions. It is worth pausing to sit with the scale of it all. You began this journey as a person sitting somewhere on the surface of a planet, orbiting an unremarkable star in the outer regions of a barred spiral galaxy. By now, that galaxy is one of 100,000 flowing through the Laniakea supercluster toward the Great Attractor, itself being tugged toward the Shapley concentration, while being pushed from behind by the dipole repeller. The entire local group is gravitationally bound and will persist as a unit even as the universe around it expands. Beyond the local group, on scales of hundreds of millions to billions of light years, everything is separating, accelerating, driven by a force so strange that the best minds in physics have spent 27 years trying to understand it without reaching a definitive answer. On scales larger than the observable universe, a sphere about 93 billion light years in diameter, we genuinely do not know what exists. The universe may be infinite, it may be finite and curved. It may contain structures far larger than anything we can observe, or it may be statistically similar to what we see. The observable universe is the only universe we have access to, bounded by the distance light has had time to travel since the Big Bang, and shrinking in terms of what will remain accessible as the expansion continues. There is something important to notice about where we find ourselves in this timeline. The universe is 13.8 billion years old. Star formation is still ongoing but beginning its very slow decline, with estimates suggesting another 1 to 100 trillion years before the last stars form. The cosmic web, still clearly apparent, is being gently eroded by the expansion, but its most massive nodes, the great clusters, will remain gravitationally coherent essentially forever. Dark energy has been dominant for roughly 5 to 7 billion years, meaning we are already well into the era of accelerating expansion. But the consequences of that acceleration, the isolation of clusters, the fading of the CMB, the loss of accessible information, are still billions of years away from being dramatic. We are, in other words, not at the beginning of cosmic time, and not at the end. We are somewhere in the middle, past the explosive creativity of the early universe's structure formation, but well before the slow cooling and isolation of its far future. This is the era in which gravity and dark energy are most evenly matched at the scale of what is humanly comprehensible. Local structures are still actively forming and merging, while the cosmic background quietly, steadily expands. The competition between the two forces plays out simultaneously and visibly at scales we can actually study. Everything within the observable universe is moving. Planets orbit stars. Stars orbit galactic centers. Galaxies orbit within clusters. Clusters drift within superclusters. Superclusters flow toward attractors. And the entire stage expands, carrying all of this with it, pulled in one direction by gravity and pushed in another by dark energy. The competition between these two forces has shaped every structure you have ever looked at in the night sky, and it will determine the fate of every structure that will ever exist. The Hubble tension is telling us that this competition is more subtle than our best models predict. The DESI results are telling us that the pushing force may itself be evolving. The 2025 revision of the Milky Way Andromeda merger probability is telling us that even our most immediate cosmic future is less certain than we thought. At every scale, from the local to the cosmological, the universe is quietly insisting that there is more to understand. None of this should be discouraging. Quite the opposite. Every time cosmology has hit a wall of apparent contradiction, when the expansion rate seemed to imply a universe younger than its oldest stars, when the observed density of matter seemed too low for a flat geometry, when the supernovae turned out to be too dim, the resolution revealed something genuinely new and important about the nature of reality. The Hubble tension and the DESI results are in that tradition. They are not bugs in the data. They are the data's way of insisting on being taken seriously. Where is everything going? Toward each other, locally, pulled by gravity, building structure, creating complexity. Away from each other, globally, pushed by dark energy, dismantling connection, heading toward desolation. Both things, simultaneously, at different scales, governed by different physics. And at the boundary between them, in the places where the two forces are balanced. There is a richness and a specificity to the universe that seems, in some hard-to-articulate way, exactly right for producing observers capable of asking the question. The cosmic web we mapped, the great attractor we are falling toward, the dark energy we cannot identify, the mergers playing out across billions of light years, the slow heat death waiting at the end of everything, all of it is one story. A story about matter and energy in motion, following rules that were set in the first fraction of a second of cosmic time and that are still unfolding in real time at every scale simultaneously. We are not watching that story from outside. We are inside it, moving with it, carried by the same expansion, subject to the same gravity, heading toward the same ultimate uncertainty. What gives cosmology its particular character as a science is that its object of study, the universe, is not repeatable, cannot be controlled, and exists on timescales that dwarf any conceivable observational program. We will never see the Milky Way and Andromeda complete their gravitational dance. We will never watch the Shapley concentration pull Laniakea apart over billions of years. We will never observe a black hole evaporate. We infer these things from physics we have tested in laboratories, from simulations we run on computers, from observations we make with telescopes pointed at the sky in a narrow window of cosmic time. And yet the inferences are remarkable in their scope and their consistency. The universe, studied carefully enough, turns out to be legible. It's governed by rules that can be discovered, written down in mathematics, tested against observation, and used to trace both the history that led to the present and the future that the present implies. If questions like this are the kind that keep you staring at the ceiling at 3 in the morning, consider subscribing. New scripts like this one drop regularly, and there are a lot more answers still to chase.